ഓക്കെ മക്കളെ, നമുക്ക് അടുത്തത് സ്പെക്ട്രത്തെക്കുറിച്ചുള്ള കാര്യങ്ങളിലേക്ക് വരാം. സ്പെക്ട്രം എന്താണെന്ന് നോക്കാം. ഓക്കെ, ഒരു ബൗണ്ടഡ് ലീനിയർ ഓപ്പറേറ്റർ നമുക്ക് തന്നിട്ടുണ്ടെങ്കിൽ നമുക്ക് അതിൽ കോംപ്ലക്സ് നമ്പർ സിസ്റ്റത്തിന് രണ്ടായി ഡിവൈഡ് ചെയ്തെന്ന് പറഞ്ഞു. ഒന്ന് റെഗുലർ പോയിൻറ്റ്സ്, അതായത് എ മൈനസ് ലാംഡ i ഇൻവെർട്ടബിൾ ആവുന്ന കേസും എ മൈനസ് ഐ ലാംഡ i ഇൻവെർട്ടബിൾ അല്ലാത്ത കേസും. ഓക്കെ, അപ്പോൾ വൺ ഈസ് ദ കോംപ്ലിമെൻറ്റ് ഓഫ് ദി അതർ. അപ്പോൾ റോ ഓഫ് എയുടെ കോംപ്ലിമെൻ്റ് ആണ് സിഗ്മ ഓഫ് എ ആൻഡ് വൈസ് വേഴ്സ. ഓക്കെ, തിരിച്ചും പറയാം. അപ്പോൾ ഇനി നമ്മൾ നെക്സ്റ്റ് നോക്കാൻ പോകുന്നത് ഈ സ്പെക്ട്രം മൂന്നായി തിരിക്കുന്നു എന്നുള്ള കാര്യം പറഞ്ഞു. അതിന് മുന്നായിട്ട് നമ്മൾ ഈ സ്പെക്ട്രം എന്ന് പറയുന്നത് സിയുടെ ഒരു ക്ലോസ് സബ്സെറ്റാണ് ഇൻ ടേംസ് ഓഫ് യൂഷ്വൽ മെട്രിക്. യൂഷ്വൽ ഡിസ്റ്റൻസ് വെച്ചുകൊണ്ട് നമുക്കത് ക്ലോസ്ഡാണെന്ന് പ്രൂവ് ചെയ്യാം. അത് സിഗ്മ ഓഫ് എ ക്ലോസ്ഡാണെന്ന് പ്രൂവ് ചെയ്യുന്നതിന് പകരം വി ക്യാൻ പ്രൂവ് ദി കോംപ്ലിമെൻറ്റ് ഈസ് ഓപ്പൺ. To prove rho of A is open, it is enough to prove that every point of rho of A is an interior point. So let us consider one of the point in the rho of A or sigma of A complement, lambda element of sigma of A complement. That means lambda is a regular point. Regular point means A minus lambda is invertible. So we need to find one of the radius epsilon in such a way that the neighborhood of epsilon neighborhood of that lambda is a subset of rho of A or sigma of A complement. That's what we have to prove here. Here we choose epsilon equal to 1 divided by norm of A minus lambda I inverse. This is a very important point here, the choosing of lambda. Okay, sorry, not lambda, actually epsilon or radius. Epsilon equal to 1 by norm of A minus lambda I whole inverse. It should be positive and it is an existing value because A minus lambda is invertible. Let us consider one of the point from the ball centered at lambda with epsilon radius alpha. So by the definition of the neighborhood, norm of or modulus of, because we are using the usual norm, so modulus in complex plane, so modulus of lambda minus alpha less than epsilon, but epsilon is equal to 1 divided by norm of A minus lambda I inverse. Now look at norm of A minus lambda I minus A minus alpha I. Actually we are going to prove that alpha is a member of rho of A. That means alpha is a regular point. That is what we have to prove. For that purpose A minus lambda I should be invertible. And now we consider norm of A minus lambda I minus A minus alpha I. But A cancel, so you got norm of lambda minus alpha into I, which is equal to modulus of lambda minus alpha, because it is a complex number, into norm I, because I is an operator. Okay, which is equal to norm of alpha lambda minus alpha, because the norm of the identity operator is equal to 1, which is less than epsilon by our choice of alpha. So we got what? Norm of A minus lambda I minus A minus alpha I. We take A minus alpha I is B and A minus alpha I as A, then norm of A minus B less than 1 divided by norm of A minus alpha I inverse. By the property 3 of the invertible operators, we got what? The second term, A minus alpha I is invertible. So it is a member of, alpha is a member of the regular point system, rho of A or sigma of A complement. But we choose alpha as an arbitrary value. So all the points of n epsilon of lambda is a member of sigma of A complement. Therefore every point is an interior point. That means rho of A becomes an open set in C. So rho of A is the complement of sigma of A. So sigma of A is closed in C. It's easy, I think. And next we are going to look at the proposition 5.0.1. It is discussing about the geometry of the regular points outside the region norm A, the region with region centered at origin with the radius norm A. That means if we consider the complex numbers outside the circular disk centered at the origin with the radius norm A, then all that such points should be a regular points. That means if norm A less than mod lambda. That means lambda is outside the region of the disk centered at origin with the norm A radius. Then lambda should be a regular point. That is what we have to prove here. So we take our A as a boundary linear map, and lambda is a complex number which satisfies norm A less than mod lambda, or mod lambda greater than norm A. We need to prove this lambda is in the regular point system. Actually, by the geometry of this lambda, it is outside the region, what I said earlier. Lambda is a regular point. To prove lambda is a regular point, we need to prove that what A minus lambda is invertible. But we have mod lambda is greater than norm A means norm of 1 by lambda into A is less than 1. That means norm of something is less than 1 means by the property 2 of invertible operators, I minus that is invertible. Here that value is 1 by lambda into A. That means I minus 1 by lambda into A is invertible. This implies lambda into that's also invertible. Scalar multiple of an invertible operator again invertible means lambda into that means lambda I minus A is invertible. This means A minus lambda is because a minus of that is also invertible. So A minus lambda is invertible. Therefore lambda is a regular point. Actually this is the special important one because from the picturization of this theorem you can see that the complex numbers outside the region of the circular disk centered at origin with norm A radius all belongs to the regular point system rho of A. Next we are going to classify or characterize our spectrum into three parts. First part is called the point spectrum, second one is called the continuous spectrum, and third one is called the residue spectrum. First we are going to discuss about the point spectrum. Point spectrum means actually eigenvalues. That means sigma of A consists of all complex numbers satisfies A minus lambda is not injective. A minus lambda is not injective means the kernel of A minus lambda I not equal to the trivial vector space singleton 0. That means there should be a non-zero vector x which satisfies the kernel condition. That means A minus lambda of x is equal to 0. That is Ax is equal to lambda x for some non-zero quantity x in x. Okay, so this lambda is an eigenvalue means the corresponding x is called the eigenvector, and the dimension of the kernel of A minus lambda is called the multiplicity of the eigenvalue lambda. You should note that the spectrum, point spectrum, sigma p of A is also part of our spectrum. In case of the finite dimensional spaces, we have only the point spectrum. That means sigma p of A coincide with the sigma of A. Because if lambda is not a member of sigma p of A means lambda k minus lambda is not injective. But in case of finite dimensional space, every injective map is surjective. So not injective means not subjective. So it is not invertible. That means it should be a regular point. Therefore sigma p of A must be equal to sigma of A. Okay. Next there is an important lemma 5.1.1 which deals with the linearly independent property of the eigenvectors with respect to distinct eigenvalues of the boundary linear operator. Here A is a boundary linear operator and you are given a finite number of distinct eigenvalues lambda 1, lambda 2 up to lambda n, and x1, x2, etc. xn are the corresponding eigenvectors and they are non-zero. Then they should be linearly independent because zero vector is always an eigenvector for every eigenvalue. So we consider only non-zero vector because we are going to discuss about the linearly independent property. Any set contains singleton zero should be, or zero vector should be linearly dependent. So we consider only the non-zero case here. Okay. So we are going to prove that what the distinct eigen values provides linearly independent eigenvectors. We consider finite number of eigen values of distinct eigenvalues of a boundary linear operator A, and x1, x2, etc. are the corresponding eigen vectors of A. That means Axi equal to lambda xi. We need to prove that they are linearly independent. If possible, that it is linearly dependent. That means the summation sigma equal to 1 to n alpha xi is equal to 0 means at least one of alpha I not equal to 0 by the definition of linearly dependency. Here we choose the first vector, the scalar corresponding to the first vector lambda 1 not equal to 0. We can use any of the vector, but here we fix alpha 1 not equal to 0. That means alpha 1 x1 plus the remaining thing sigma I equal to 2 to n alpha xi equal to 0 with alpha 1 not equal to 0. To prove this, we consider one of the polynomial p of lambda which satisfies the condition that p of lambda 1 equal to 1 and p of lambda equal to 0 for I varies from 2 to n. That means n minus 1 eigenvectors are the roots of the polynomial p of x. Okay, here p of x is equal to a0 plus a1 x plus etc. an x raised to n with a n not equal to 0 n degree polynomial with p of alpha 1 lambda 1 equal to 1 and p of lambda is equal to 0 for I varies from 2, 3 up to n. Now what is p of a? P of a is equal to a0 I plus a1 I plus etc. an a raised to n. Here actually x raised to n, it is not true. Actually a raised to n, capital A raised to n. A raised to n means a composition up to a n times. So p of lambda is equal to a0 plus a1 lambda 1 plus etc. plus an lambda I raised to n. Therefore p of a into xi is equal to p of a into xi. We just substitute the value a0 I plus a1 a plus etc. plus an a raised to n into xi, which is equal to a0 into I xi plus etc. From this condition we get p of lambda I into xi. Is easy, I think. Now look at 0 into p of a, but 0 equal to summation that our summation alpha 1 x1 plus summation I varies 2 to n alpha xi, which is equal to 0. Just substitute that value and multiply p of I with all these quantities, distribute using distributive law. So you got alpha 1 p of a into x1 plus sigma 2 to n alpha I p of a into xi. Just substitute the above value p of lambda into xi here. So alpha 1 into p of lambda 1 x1 plus sigma 2 to n alpha into p of lambda I xi. This means 0 equal to alpha 1 x1, but you know x1 not equal to 0 implies alpha 1 is equal to 0, which is a contradiction. That means our collection should be linearly independent. Therefore the eigen vectors corresponding to distinct finite number of eigen values should be linearly independent. That is our lemma. Next, look at the continuous spectrum. Here continuous spectrum sigma c of a. In continuous spectrum a minus lambda is injective and image closure equal to x. Image closure equal to x means actually image a minus lambda is not equal to x. You note that it is not surjective at a time, because if it is injective as well as surjective, then it automatically it becomes invertible, but note that image of a minus lambda is not equal to x here for continuous spectrum, because continuous spectrum is the part of the spectrum. And in case of spectrum a minus lambda is not invertible means either a minus lambda is not injective or a minus lambda is not surjective. Here a minus lambda is injective is given, so automatically surjective property is not possible. That's why I said what image of a minus lambda is not equal to x, but its closure equal to x for our continuous spectrum. That is the importance of the definition of continuous spectrum. That means image is dense in x but not equal to x. Not that. Here we have an important operator on capital L2 space, L2 of closed interval 0 1 defined by a of x of t equal to t into x of t. Note that x is the two integrable function, and in case of this the continuous spectrum and spectrum coincides with the closed interval 0 1. Okay, this is one of the example for our continuous spectrum. The next one is the residue spectrum. Residue spectrum and continuous spectrum. Here note that continuous spectrum and the point spectrum are disjoint. That means sigma c of a intersection and sigma p of a should be empty. And residue spectrum, in case of residue spectrum we consider a minus lambda is injective and the closure not equal to x. That means it is a closure is a proper subset of X or proper subspace of X. So image A minus lambda I closure is a proper subspace of X. So sigma R of A does not intersect with sigma C of A. That means sigma R of A intersection sigma C of A is empty, and sigma R of A with sigma P of A is also empty. Now, that means all these three spectrums are disjoint, mutually disjoint. So the spectrum divided into three parts: point spectrum, continuous spectrum, and residue spectrum. In case of finite dimensional spaces, for any boundary linear operator, the point spectrum coincide with the spectrum. So automatically sigma C of a continuous spectrum and residue spectrum should be empty. Next we consider our right shift operator, which is injective, and for that right shift operator, it is injective. So A minus lambda I injective for every lambda element of C. That means in case of the right shift operator, the point spectrum is empty. That means right shift operator has no eigenvalues here, because A minus lambda is always injective. So it has two parts, lambda C of A and lambda R of A. Here we didn't discuss about the continuous spectrum. We discuss only about the residue spectrum. Sigma R of A is equal to the unit circle, unit open disk in the complex number system, set of a lambda element of C such as mod lambda less than 1. So notice that for the right shift operator, sigma P of A is empty, sigma R of A is the unit open disk. Okay, centered at the origin. Next, look at the point spectrum, residue spectrum, and continuous spectrum of the special operator on capital L2. That's what we discussed earlier. A of x of t equal to t into x of t. In that case, spectrum and continuous spectrum coincides, and it is equal to closed interval 0, 1, and other two spectrums, sigma P of A and sigma of R of A, are empty. Okay. Next we discuss the theorem 4.1.1, which states that the X is a normed space and Y is a complete normed space. Then the